before we start, okay, I would like to introduce our speaker for today, which is Dr. Uy Kai. I believe Dr. Uy already in this link. Hi, Dr. Uy.
Hi, afternoon, everyone.
Dr. Uy.
Hello. Yeah, afternoon. Can you guys hear me?
Yes.
Uh,
Yeah.
okay, I will proceed with the introduction of the speaker. So Dr. Uy is actually a principal product specialist in material characterization from Bukit Arang. He received his PhD from UTM in the field of material science and analytical instrumentation in 2016. And his current role in Pekin Elmo is performing research and laboratory work, project management, field applications development, software and data analysis, as well as business strategic planning. Okay. All right. So this is the tentative for today. First, we will have our welcome remarks and introduction to speaker, which I've done previously. And then after this, we will proceed with the presentation by Dr. Uy. And after this session by Dr. Uy, we will have a video presentation of the preparation of TGA and DSC by Madam Faiza. And after that, I will explain on the booking procedure through ULAB, and we will end our webinar is expected at 5 p.m. Right. So upon completion of this webinar, the participants will be able to understand the basic principles, instrument setup, sample suitability and sample preparation, data analysis and interpretation, application of the analysis, as well as the booking procedures through that. Right? So without further ado, I would like to invite Dr. Uy to continue his sharing.
Thank you. Thanks for the. Yep. Thank you. Thanks for the introduction.
Dr. Uy, I couldn't hear you.
Oh, okay. Can you hear me now? Wait.
Can anyone hear Dr. Uy?
Yeah. Can
Yes.
anyone hear me?
Yes, I'm here.
Yes, we can hear.
Okay. So I'll proceed and I'll share my screen now.
Okay.
So can everyone see the screen?
Yes.
Okay. Good. So for today's discussion, we'll be focusing on TGA and also DSC. So feel free to stop me if you have any questions, or we can discuss this after the presentations. So it will be separate into two sessions. I'll start off with TGA first, thermogravimetric analyzer. Then the second part will be proceed on to DSC, differential scanning calorimetry. So of course, different instrumentation will do different things. So I will go through the hardware, the designs of it, what you can do with different instrumentations, then what are the data that you can obtain, okay, for your materials. So for thanks to UTP for the invitations and everything. But for the discussion and everything will be more of a general discussion. So I will talk from the material point of view. Okay. So what is thermal analysis? So of course, the technique is you're dealing with the changes of the physical properties of the materials measured against the function of temperature or time under a control temperature or time program. Let me call my pointer. Okay, now, so the working principle is, regardless of what technique you are using or what thermal instrumentations that you are going through, it should always be in a control temperature and time program. So when we talk about control temperature or time program, means there is a control heating rate or control cooling rates that you have, you are running the instruments. So it's degree C per minute usually. Okay, so that is the heating rate that we can control. So of course, if you are going to study the heat flow of the material, whether the transitions is endothermic or exothermic, then that's the job for DSC. Okay, so here I shows you the instrument DSC 8000, okay, from the latest offering from PerkinElmer. And then we have TGA, okay, measuring the weight losses or the decompositional temperature of the material itself. This is TGA 8000. Then you have thermomechanical analyzer, TMA, so looks like this. So this measures the dimensional changes of the material. So as a physical phenomenon, when your material is being heated or being cooled, it will expand or contract, okay? So TMA is the job to measure the dimensional changes of the material. Then you have DMA, dynamic mechanical analyzer. So this looks like this, DMA 8000. So the job is to measure the viscoelastic properties of the material. So these two I'm not going to go deep into here. The main focus will be discussing on these parts. Okay. Now we have another type of instruments. I wouldn't say another type, but we call it STA, simultaneous thermal analyzer. So STA, the job is actually you are running it like a TGA, means you're getting the weight loss information and everything, weight changes. But at the same time, it also gives you the DTA signals, means the heat flow signals. But make no mistakes, if you are going to study those weak transitions materials, for example, glass transition temperature, usually it's a very weak signal transitions, it is always better to go with a standalone DSC. So for STA, what is the purpose of it, for example? So for example, you are looking into glass vitrification temperature, means the glass fusing temperature, okay, which is usually occur at very, very high temperature. Or if you're dealing with colonite or ceramics, as we call it, so what is the firing temperature, okay, for your clay? What is the phase transitions at above 1000 degrees C, for example? So that is the job of STA, okay, means at high temperature, because for DSC, usually we don't do sample decompositions, okay? So, and the maximum temperature that you can heat up to is not more than 800, which is more than enough already, because most of your organic materials or polymeric materials will start degrade at 450 to 500 degrees C. Okay. Oh, going back to DMA 8000 just now. So DMA 8000, it measures the viscoelastic properties of the material. So a good material to study using DMA will be your rubbers. Okay, means your elastomers. So it measures how many parts or which parts of the material is actually viscous, which part of it is actually um, the elastics. Okay, so you can get the information. So usually people use it to represent TG as well, because TG is a weak signal. You might not see it under DSC. So now you have DSC. So it looks like this. So what are the informations that we can get from DSC? Usually is TG. Okay, TG usually occurs at lower temperature. So sometimes for semi-crystalline materials, so these are the terms or the things that later we can go further into it. You might encounter a crystallization peak, okay, or what we call as a co-crystallization peak. Now this is doing heating. So this is actually the reorganizations of the molecular chain within your materials. And then, of course, this is melting. So the way we read a heat flow chart or the thermogram, okay, from DSC, or if you have a STA, the DTA signals, always read from your y-axis first, because it can be indication of endo up or endo down. Okay, so make sure your y-axis is in the correct orientation. For example, here shows endo up. That means this is endothermic, this is endothermic, this is exothermic. Okay, because endo up. So if endo down, then this all thing will be vice versa or inverse. Okay. So this is your melting, this is crystallization, this is glass transition temperature. Hence heat flow versus temperature or time. As what I've mentioned, why you do have the time profile, because you are now heating your sample under a control heating rate. Okay, so you get your melting temperature, crystallization temperature, glass transition temperature, depend on your sample nature. Now, again, for thermal analysis, is not a tool for you to do identifications. Okay, it's more like a characterization tools. Means I understand what my material is, but if I modify my material, or if I add more of certain materials into my material, what happens to the performance of it? What changes to the properties of it? Okay, so then the thermal instrument will give you the analysis of that or the feedback from your material. So it is not to run blank sample or blind samples, or we call it as. So if you want to do identifications, and this is especially dangerous if you have a standalone DSC and you run it blindly, because if you run until it decomposes within your furnace chamber, then of course contamination is going to happen, and also you're going to damage the furnace itself as well. So before subject to a DSC scan, you should always run in TGA first to determine what is the safety temperature, or what we call as the decomposition temperature. Now, you do see that for DSC, we don't deal with weights, but regardless, you need to key in your weight information as well, because your peak area or your enthalpy, okay, depends on the weight that you are using or the mass of the samples, okay. Of course, you can do curing as well. For example, like thermoset material, the epoxy, or your resin material, acrylic paint, all these things that tends to cure over time. You can use DSC to check as well. What is the curing time? What is the curing degree? Then you can run reaction rate, kinetics as well using the software, the advanced software that supplied together with the DSC. Or this is a standard method, we call it OIT, oxidation induction time. Then you have your TGA. Of course, TGA plays with or measures the weight losses of the material. So what other informations that you can get from here? Your decomposition temperature, weight percentage of each component. So how many steps of losses that you observe here, representation of how many components within your materials. And as what I've mentioned, so for thermal analysis, regardless TGA or DSC, it wouldn't tell you what it is. So it is a characterization tools. It is not a identification tools, okay? So if you have an oxygen, of course, you can do oxidation time as well. So, or for those dealing with any carbon materials, okay, for example, like graphene, CNT, or even if you want to do like your catalyst poisonings analysis, okay, the coke depositions or the deactivation of your catalyst, oxygen is required, because carbon is actually very stable even at very high temperature, whereby you do need oxygen to react with carbon. We call it combustion processes and release as. So you're going to observe another weight drop when there is oxygen in contact with carbon and released as a carbon dioxide. Okay. So these are the instruments that PerkinElmer actually offers. So for DSC, we do have two different techniques. One is the heat flux technique, DSC 4000, 6000. Another one is DSC 8000, 8005. So these are the power compensation, which is PerkinElmer proprietary techniques. Then the conventional DSC that you're going to see on the market, or what we call the conventional DSC, is the heat flux DSC. Okay, so what's the difference? Later I'm going, we can explore more on that. Then as for TGA, also two models, but the main purpose is still to get you the weight losses, and also what is the decomposition temperature or the time of it. Now, what's the difference beside the design of it is the sensitivity of the balance. So TGA 8000 has a 10 times more sensitive balance compared to TGA 4000. So in all your TGA, regardless of the models, there's a built-in balance inside. Okay, so this is what we call as a top loading TGA, whereby you put your sample on top, your balance is at the bottom. Hence, it's called top loading. Then you have a bottom loading TGA. This is where your balance is situated. This is where the sample is located. Okay, so it's hang down from the balance. Hence, it's called bottom loading TGA. And this is the one that I mentioned just now, STA. We call it simultaneous thermal analyzer. So it simultaneously gives you a TGA, the weight loss curve, and also the DTA signal, means the heat flow curve. Okay, but if you want a very accurate temperature control, or very strong signals from the transitions of your materials, it is always recommended to go with a standalone DSC. Okay, but if you are studying phase transitions at very, very high temperature, then the option is to go with STA. Okay, then DMA. Then all our TGA can be hyphenated. This is another thing that we can discuss more, that you can hook it up with another instrument in one single run. So you can hook it up with IR, or you can hook it up with GCMS as shown here from TGA. We call it evolved gases analysis. So not only you get your quantitative results and also qualitative results in one single run, means the gases that coming from your TGA, now you can flow into, for example, GCMS or even IR to do further analysis, okay, in real time for IR especially, okay. So we start with TGA first. So of course, this is the typical results that you're going to get. We call it thermogram. Now, it wouldn't, of course, it wouldn't tell you this is volatile, this is oil, this is polymer, this is carbon. These are based on the molecular weight of the material itself. Then we can do a rough labeling. Okay, now it wouldn't tell you what type of polymer it is, but as what I've mentioned just now, typically polymer decomposes, as you can see from here, from 400 something up to 550 usually. Okay, most of the polymer. And although we say that TGA is suitable for organic materials, you can run inorganic materials as well. So TGA is actually a very versatile instruments. You can run pretty much any samples that you would like to see. Okay, so we can discuss that during the application. So of course, the sample with a lower molecular density or molecular weight is going to decompose first. Hence, usually less than 200, what you are going to get is usually your volatiles, whether it's oil, is your moisture, or is your solvent, residual solvent. So some people use TGA to do residual solvent analysis as well. Okay, so usually, so you do need a sensitive balance to read that if that's the case. Hence TGA 8000 with a 0.1 microgram ultra micro balance. So to measure a very, very small or very, very minute changes within the weight masses or within the weights of your samples. So TGA, the main purpose is measuring the changes of the mass when it is heated, cool, or being held at a isothermal temperature. So you can do isothermal as well. Okay. So this is the specification. Maximum temperature, you can go up to 1200 degrees C. So this is the microbalance that you can read, so 0.1 microgram. Okay, so the lower the value here or the resolution here, the smaller the transitions that you can actually do. Okay, so this is the, yes, any questions? Okay, now this is the cross-section diagram of the TGA 8000. Okay, so this is the sample pan. Your sample is going to be situated here. This is your furnace. This is the thermocouple. So how we read the weight is, this is what we call as a hang down wire. So you're going to load your sample. The whole thing is going to be hooked up on top of it and it's going to drag down it. And then how much light that the photodiode receive. Okay, there's a LED light here. How much light it receives, the sensors will translate into how much weight of your sample masses. So you do not need an external balance to read the weight of your sample. You can use the balance built in to read the weight. I mean, as per any TGA run, you need to tare zero first and then tare your sample weights. Okay. So what enhances the sensitivity of the instruments from Perkin-Elmer's design? Okay, so we have a balance chamber temperature control, isolated balance, and then balance isolations, anti-convection systems, and also to eliminate the statics. So this is what the balance looks like. Okay, so now just now the hang down wire that you see here is passing through here. Okay, so this is the balance beam. This is the balance beam. Now this whole balance compartment is sealed off. Okay, so it's isolated and is maintained under a constant 42 degrees C. Why is it so? Because you do not want your balance beam to expand or contract according to your environmental temperature, especially if your environmental temperature tends to fluctuate throughout the day. Okay, so with this PID control, it's constantly maintained at 42 degrees C, so that regardless what you're doing, you can always, or at any given time, any given temperature, you will always get the most accurate weight reading of your sample. Okay, remember TGA, the most important thing is we are measuring what is happening to the weight that occurring onto your samples. Okay, so this is what we call as an iris. So this is the hang down wire that's passing through just now. Okay, to look to hold your sample on top. Now you can close it, the aperture, you can close it like a camera, you can close it to a very, very small just to let the hang down wire pass through. So what's the purpose of this is when you do a heating, like TGA, we are doing high temperature analysis or there's a temperature decompositions. So when temperature decomposes, it's going to become gas and then it's going to go up and go into your balance if there is no purge gases, okay? Because it's now lighter. So with lower density, it's tend to go up. So this will actually block off the gas that's coming out from your sample chamber going into the balance and contaminate your balances. And also it reduces the influx of heat from furnace to the balance chamber. Means the heat, when we are doing heating, will not go into your balance as well, causing expansion of the balance as well. Okay. Then we have anti-convection. Okay, now anti-convection is something that is a normal phenomenon, but it's something that we don't want in TGA because this will give false positive or false negative results. Okay, caused by the air turbulence or the purge gas turbulence. So now in TGA, usually we are using nitrogen gases as a purge gas. So the gas that coming in from the tank or from the nitrogen generator usually is a cold gases. So when your sample chamber is heated up, it will take time for equilibrium. Okay, so for those, if you notice that how the fire or the light or your matches or your candle, how it burns, it's like your flame is always like a water droplet. Okay, why is it so? Because this is due to convection. So the air being heated up, it will become lighter, it will go up, and then the void will be replaced by the surrounding air or the surrounding gases. Hence, it's causing it to be like a water droplet. So this thing also happened inside of TGA as well. So the lighter gases being heated up, lighter nitrogen going up, and then being replaced by the gas from the surrounding. But this will create what we call as a buoyancy effect, okay, causing subtle weight changes, okay, or the fluctuation of the weight, which we do not want that because it doesn't reflect or coming from your sample. So by putting it what we call as a chamber sleeve, the quartz chamber sleeve, you can reduce or regulate the convection effects, okay, that happening. So this will reduce the uncertainty and result in greater sensitivity towards the weight changes. So for those running a lot of powder sample, fiber sample, thin film samples, so when you're running this type of solid materials, usually it generates lots of statics. So the static actually will cause the pen to stick to the side of the furnace, causing the weight reading error. So when the glassware is being raised up, so we have ion stream static eliminators to remove all the statics generated. So how it does is, so the gases, the nitrogen gases coming from the, whether you are using a tank or generator, will pass through a high voltage wire and become ionized nitrogen gases. So this thing will actually raise up. Remember, this is your sample pan. Your sample is going to be here. So before it raises up, this ionized nitrogen will purge all your glassware, neutralizes all the static charges. And then when you raise all this in a sealed environment, this thing will be still free hanging, okay, without touching the side of the furnace. Okay, so this is another things that protects your data integrity. And we have a rapid and safe cool down that takes from 1000 to 40 degrees C in less than 15 minutes without any water chiller required. Okay, for this model TGA 8000. Okay, this is the features. So you have a 48 position auto sampler, very, very small, as you can see from here at the side of it only. Okay, and you can even hook it up with, at this moment it's only iOS systems, but you can use a pad or iPhone to control your run or monitor the conditions of your instruments. Okay, and with the light illumination from afar, you can actually tell what is what methods or what steps your instrument is actually running. So if it's red, it's doing heating, blue is doing cooling, green is doing isothermal. Okay. So we have another accessories called GMD. So all our TGA have a built-in MFC. Okay, we call it mass flow controller. So now beside the heating rate is something that we can control, or what is the temperature range that we can heat up to. Another thing that we can control is what we call as gas flow rates or the purge gas. Okay, so in TGA, most commonly we are using nitrogen, but some people use oxygen as well. But nitrogen is a must because your balance requires purging as well. So you can see inside there, there's a 2 MFC built in. So from the balance is separate purge. Okay, so this is always inert gases, usually nitrogen. You can also use helium if you want to. So this is going to the balance. So A and B, one is for inert gases, one is for active gases, usually, or reactive gases, usually oxygen. You can use other types of gas as well. But at any given temperature or time or any steps, only one of the gas that's going into your sample chamber. Now, what if I want to do multiple gases analysis, or I want to mix my gas in a certain ratio or certain compositions. So it allows you to do simulation studies, for example, okay, in different proportions of gas, mixing up to 3 types of gases using this accessory, GMD 8000. So it looks like this. So inside the GMD 8000, there's its individual MFC. Now you can connect different gases to it. So now, example, I have nitrogen, argon, and oxygen, and the percentage I can control in a mix. Now, do not confuse with purified air. Purified air is already pre-blend or pre-mixed, so you cannot control the ratio, although it is a mixture of gases, but the ratio is constant. So with this accessory, you can choose whatever type of gases that you would like, and also what is the percentages that you can control. Okay, so now you can flow in with a mixtures of gas A and B and C in certain proportions, or you want to flow it individually. There's no problems with that as well. Okay, using these accessories. So usually people use it to do simulations under different percentages. Maybe they want to study the reactivity of the materials. They will change, for example, in oxygen's conditions, if different percentage of oxygen, what happens to the materials itself. Okay, so you can use this to do a simulation studies. So of course, like what I mentioned just now, regardless whichever model you're going for, TGA, DSC, or even STA, inside there's is individual MFC, mass flow controller. So provide you gas switching capability, automated. You just need to program it inside the software. Okay, provide you precise gas flow rates. So the rate by default that we are using is 20 mil per minute. So everything is controlled by the software. So the type of gases that we normally use, okay, for sample, you can use nitrogen, you can use air, you can use oxygen, but for balance always nitrogen or helium means only inert gases, okay? Now, flow rates, 20 mil per minute. For balance, usually we recommended double so that to force every gases that's coming out from the balance chamber, from the sample chamber, to go unidirection to the exhaust, okay? Because the purge will happen from balance, go down to the sample or the furnace, okay? Now this is the cooling configuration. So if you have other types of models, for example, like STA or TGA 4000, then you have then you need to go with a chiller. TGA 8000 are optional, so that you do not overheat the furnace itself, okay? So depending on what are the coolants that you put into your chiller, you can start your analysis temperature at this, but the lowest that you can go for TGA is -20, though usually people starts at ambient temperature, okay? So with water, for examples, you can start at lowest at 10. So if you mix 70% water, 30% e.g. ethylene glycol is a coolant, you can start at 0. So now the water doesn't froze over at 0 degrees C, okay? So if you mix 50% e.g. on H2O, then you can start at -20, okay? So these are things that you need for TGA run. So this is the pens that we offered, okay, for different analysis or different requirements. So we do have a platinum pen, and we usually people use ceramic pen because this is chemically inert. It doesn't react and it can withstand high temperature. The trade-off is ceramic by itself is thermally isolated material. So if you want to have a better thermal conductivity for your materials, then you need to go with a platinum pen. Okay, but usually ceramic is more than enough for all the general applications. So next will be the applications. Okay, so what are the things that we can do with TGA? First, of course, like what I mentioned just now, you can do compositional analysis. How many steps that you observe, step decreases of the weight, represent how many components within your materials. So measurement of the volatiles, you can do your solvent analysis, water, moisture, for example, the surface moisture, or even interstitial moisture with the increment of the temperature, okay? Then of course your oil as well for those running that. Then carbon black, this usually for polymer people that they use carbon black as a strengthener or additives, okay, into their polymers. Or for those running, for example, graphene, graphite, elastomers, then you do see these as well. But in order to do this, oxygen is required. Then you have your decomposition temperature coming from the weight loss or your thermogram. Then thermal stability means how well can your materials, the higher the temperature that your material starts to decompose, the higher the thermal stability it is. So oxidative stability requires oxygen as well, means how long can the material sustain oxidation, okay? Then reaction kinetics. So the kinetics for TGA, we are using 6 curves methods. What we call is a minimum 3 curves method, hit at different heating rates. So if you want to do kinetics to simulate what is the shelf life of the materials, okay, then you can use TGA to do that as well, to do the predictions. So typical curve that you are going to get, or typical thermogram that we are going to get, is something like this. All these are rubber materials, okay? But as you can see, in general, the decomposition mechanism mostly is the same. So you start off with volatile first, definitely, because this will have the lowest molecular weight. Then after that, going to the polymer region, okay, for all these elastomers. So now, when you heat from, for example, like room temp all the way up to 700 in nitrogen purge, this process, we call it pyrolysis, okay? Means there's no oxygen coming into contact. Polymer pyrolyzes from, when we talk about decomposition, means it's from very complex or very high molecular weights becomes very simple form. Usually we call it carbon. It's like you're cooking a material or you're cooking a chicken, okay? So if you cook it up too fast at a very, very high temperature, what happens is become char, okay? And that is actually carbon, a relatively simple form of carbon. So this is the things that happen to your polymer as well. So your polymer will become shorter and shorter chain, become simpler and simpler form, and usually is carbon. And hence, if you do not have any oxygen, you are going to notice that the weight is getting more and more stable, but after that, when you run all your analysis, you'll notice that all your pen become black color due to the carbon depositions onto your pen, your sample pen, okay? And hence, these steps only comes out if there is oxygen, which we call it a combustion process. Carbon plus oxygen releases or weight loss as a carbon dioxide. Okay, so the residual that doesn't remove, we call it ash. Usually is the inorganic fillers that's been added into the materials. Okay. So this is another one that they use TGA to check what is the solvent depositions onto the PCB, so printed circuit board, okay, in your semicon industry. So they can't afford any volatiles depositions onto the PCB because this will cause voids and causing malfunction. Okay, so the way they do this is they hold isothermal at 120 degrees C for 15 hours and monitor what is the weight losses. This represents the solvent, the residual solvent that's deposited onto a PCB, and there is a threshold limit or acceptance limit. Okay, you cannot go too, if there's too much means the QA/QC has already failed. Okay, so with the very, very sensitive TGA, you can detect very, very low levels of volatiles. So this applies not only to your solvent, it can be moisture as well. Okay. So the one that I mentioned just now, people use TGA mainly to check the filler content, especially industrial. Okay, so filler is something that they put into the polymer, for example, okay, to reduce the cost or to modify the performance of the material, whether regardless of thermal expansion, the stiffness of it, and then the damping of the final products. Okay, so in terms of electronics, this is important that it affects the CTE. Okay, so example, if you are using your phone or your electronics, sometimes you notice that it's getting hotter and hotter when it's running. So as what I've mentioned, material will expand, okay, when the temperature goes up. So they need to measure what is the coefficient of thermal expansion of the materials. If they expand too much, it's going to peel off or it's going to become concave, okay? Or you notice the swelling of the material. This is due to the CTE is not within the permissible value, okay? So reinforcing fillers, improving the mechanical properties of the polymer, particular the mechanical strength of it. Usually they add in inorganic filler, and hence when you burn until everything is already gone, what is the leftover or residue? Usually this is the indication there's inorganic fillers being added into it. Okay. So carbon content analysis. So what this is what it looks like. So volatile oil standards, your polymers, carbon, and if there is no oxygen, flat line. If there is oxygen, this will come out, and then residual will be your ash or filler. And when this comes out depends on what is the temperature or the time that you start to flow oxygen. So if I start to flow at 700, then it will come out at 700. If 600, then 600. Okay, so this weight losses, there is no definite temperature that you start flowing. But usually what we recommend is after 650, then you switch over to oxygen, because as what I've mentioned just now, most of your polymer will decompose completely after 600 or 650. And then this is a good time for you to switch over to oxygen for the carbon analysis. So this is a standard method for running rubber materials. Okay, so as what we have mentioned just now, usually less than 300 or 200 is your volatiles, is your oils, then is your elastomers or polymer. Elastomer is also a type of polymer, like what I mentioned. Usually 600, 650, most of it is gone. So in order to analyze carbon, you need oxygen. So what else is left over? This is your fillers or ash. Okay. So I'm not sure whether you are running because since Petronas UTP, right? You are maybe running a coke analysis as well. So for the energy sources, this is for fuel analysis. So proximate coal analysis, okay? So you get your moisture content, you get your volatiles, and then switch over to oxygen to get carbon content. So this will determine what is your BTU, for example, following these ASTM methods, okay? Then this is for lube oil. Okay, this is also another standard methods that need to comply for those lube oil manufacturers. Okay, so you have a reference oil. You need to match it with. We need to sample it at a reference time. Okay, usually it's at 11.65 minutes, and monitor what is the weight losses. So you have two oils. So your oil cannot be too volatile, because if your oil is too volatile, it's going to damage the engine. As you are running your engine, right, it's going to get more and more, it's going to get evaporated, and then causing damage to the engine now. So comparatively, you can see from here, your oil samples or the oil that you being manufactured, at the same time that you are sampling for the weight losses, or monitor for the weight losses, must be smaller than the reference oil. So in this case, oil C has lower volatility compared to oil D. Oil D definitely fail, because you can see the oil losses is much higher compared to the reference oil at the same time duration. Okay. So this is for soot content using TGA as well. So again, incomplete combustions of your lube oil is actually going to form carbon. Okay, soot is actually carbon. So you need to have oxygen in order to run carbon analysis, as what we have mentioned just now. So now we monitor what is the percentage of the soot based on the standard oil. So you can use this to monitor very, very small percentages of carbon that's being formed as well. Okay, so we use a standard oil. These are the standard value, and then we verify with TGA, and you can see you can get comparable results as well. Okay, with the standards. So this is standard, means with a known soot values. Then we use TGA to verify it. And you can actually see you can get very, very close. And this is doable for high percentages, no problem if you're using a not that sensitive TGA. But as you go lower and lower, now this is where you're having a very sensitive balance we've shown you. Okay. So for TGA only, or TGA 8000 only, there's advanced software. Okay, so what this does is, okay, now first, that what I mentioned just now, you can do kinetics, right? So we have a 6 curves method in different heating rates. So only one step heating only. Okay, so this is a polyethylene material. So this is what it looks like for the TGA kinetics, or the decomposition curves of it. So 6 different heating rates, or minimum 3 if you are going to run a kinetic. Okay, so monitor the decomposition events using the time scale as well. Okay, So of course, the faster that you heat up your material, the higher the decomposition temperature becomes. This is what we call as a thermal lag effect. Why is this so? Because in order for material to decompose, each part of the material must reach the same temperature. So if you heat up very fast, means your sample cannot manage to catch up with what you're programming. It will take time for it to reach the whole part of the material to reach the same temperature. Okay, so you can see 1 degree C, because you heat slowly, your material can catch up. So there is reduced thermal lag. So now it decomposes at this temperature. But you see at 40, it pushes from here all the way to here. Okay, because now it takes this long for your material actually to reach equilibrium for the decomposition temperature. Okay, so with this raw data, you can actually use it to model the decomposition kinetics of this polymer. So just feed into the software. What you need to do is just collect the raw data. Okay, so another two advanced features that Programmer offer is what we call as auto stepwise and variable rates. Okay, provide you better separation and better resolution. How? Okay, now example, usually we want it to separate well, or what we call as a high resolution TGA. What we need to do is we need to heat it slowly. Okay, also to reduce thermal lag. So to improve resolution, use a slow and constant heating rate, or this is what people normally do. But you do this, you can see from 50 to 850 at 2 degrees C per minute, one sample is cost you 7 hours. It doesn't even make sense, right? So too long. So what we come up with is when there is, for auto stepwise TGA, when there is no weight losses, you can go fast, or you can use a higher heating rate. Okay, when it encounters weight losses, then you can reduce the scan rate to a small scan rate to optimize the resolutions, or you can even do isothermal. Okay, until when the decomposition is completed, it will revert back to its original heating rate again. Okay, so this is auto stepwise. So when there is no weight losses, it go fast. When there is, it goes slow, or it can go isothermal. Okay, so the benefit of this is you are not sacrificing your resolution in the amount of time. Okay, so you can get the same resolution or best, even better resolution in a shorter amount of time. Then you have variable rates. So variable rate, now we do not control the rates. Instead, what we control is resolution. So the higher resolution that we set, the slower it goes. So when it encounters a weight losses, the heating rate will exponentially decelerate. Okay, and then when the weight loss comes to an end, it will return to its original heating rate. Okay, so what we adjust here is resolution, but both of them the same thing. The main purpose is to reduce the time for the analysis in order to get the best resolutions as well. Okay, so this tool is the proposed that you can do. So what's the difference of this? If your sample is like, for example, polymer material or quite stable material, you can always use auto stepwise TGA. If your sample is dynamic or tends to have a sudden weight losses, then recommended using a variable rate. Okay. So oh, sorry. Okay, so just now it's the standard methods for the ASTM standard methods for petrochemicals. Okay, so you can find out more if you need to. So TGA is also widely applicable in petrochemical industry as well. Next will be DSC. So DSC, what's the main purpose of it? It doesn't measure weight losses, although you do need to key in the weight informations of the material itself. Okay, so what it measures is endothermic and exothermic events happening to your material. Okay, example, this is not polymer, but it can be polymer as well. The easiest example is your ice to your water to your vapor. So from ice, solid to liquid melting. Okay, and melting is always endothermic. So the definition of endothermic is take the heat from the surrounding into the material, kinetic energy increases, okay, free volume increases, then from solid becomes liquid, phase transition. Now, make it clear that when we are talking about decomposition and phase transition, these are two different concepts. In DSC, there is no structural destruction. Means water, when it changed to, sorry, from ice change to water, these are still water molecules, so H2O still. That means there is no from complex material into simpler form, not like TGA. TGA, when you do decomposition, means from long polymer, it cuts shorter and shorter, becomes a simpler and simpler form. So for example, like carbon, like char, like coke, okay? But not in DSC. So when you apply this onto your polymeric material as well, then you notice that your structure doesn't change or your weight shouldn't change, okay? Because there is no changes on the molecular weight, on the molecular chain or the structure of the material itself. It's just the phase that is changes, means from solid into liquid, liquid into gas. So there's 3 phases. So melting evaporation is always endothermic. Then condensation or crystallization, freezing, is always exothermic, means you releases heat to the surrounding, kinetic energy decreases, okay? Then phase transition, okay? So these are the phenomenon, okay, or the reactions that you can monitor or which it belongs to under the you can detect using DSC. Okay, so for physical phenomenon, for example, usually what people want to measure is your crystallization temperature, your melting temperature, your vaporization temperature, okay, or sublimation temperature. Sublimation means from solid straight away to liquid. For example, like solid carbon dioxide. Now, as of chemical changes, you have your oxidations. Okay, now chemical change usually is irreversibles. Okay, oxidate like oxidation. Once you oxidize, it doesn't go back to its unoxidized or deoxidized form. So it's always endothermic because, sorry, it's always exothermic because new bond being formed. Okay, decomposition. Now, this is the reason why we don't do decomposition in DSC. Okay, it can be exo, it can be endo, but most of the time it's just going to give you a lot of noise without any usable data. And at the same time, you are going to destroy your furnace, okay, or contaminate your furnace. So not recommended at all to do decomposition, and you shouldn't do decomposition in a standalone DSC units. Okay, so for STA units, although it gives you a heat flow signal like what I mentioned just now, but because it's so still treat it like a TGA, I would say. Okay, the main purpose is still to give you decomposition temperature, but at the same time, additional heat flow informations can be obtained. But since it's going to do decomposition, of course, as you can see, it can be ISO, it can be endo. So when it encounters decomposition, usually the heat flow is going to get up or down depending on what type of transition is going to happen. Okay, so if you are looking into a, for example, TG or melting or crystallization, a very precise of it, results of it, then standalone DSC will still recommended. Okay, on curing as well. So irreversible means from monomer into your polymer. Okay, usually this is referring to cross-linking, new bond being formed as well, condensation, water is precipitated, then it's also an exothermic event. Okay, so those playing with resins or acrylic materials, this type of material is actually curing, or from semicon industries, those doing adhesive or your hard disks, whereby they cannot use solvent to cure the materials or temperature to cure the materials, they will use UV curing. Means your material is going to cure under UV light. Okay. So DSC also we have 2 technologies as what I mentioned. So the conventional is what we call as a heat flux technology. Okay. So heat flux means the reference and your sample. So now you notice what's the difference just now. TGA, the sample container or the sample holder is actually made from ceramics, whereby and ceramic by itself, as what I mentioned, it is a thermal insulators. Okay. So now for DSC, what we do is, or what are the sample container being used is actually aluminum pan. I mean, classically or conventionally, you do have other types of pens for you to choose from as well, depending on your applications. But typically, we are using aluminum. And notice that this is not an open compartment analysis. Everything is encapsulated. So these are the main differences of standalone TGA and also DSC. And of course, the information that you're going to get is going to be different as well. So I would say these two are complementary techniques. Okay. So for heat flux technique, both your reference and your sample needs to be put into the single furnace. And in fact, there's only one furnace inside. Okay. So compared with TGA, you do not need to have a reference, right? For DSC standalone, you do need that. Okay. So now, as you heat up across the time, temperature goes up. Okay. In your reference, there is no sample. So this is heat flux principle. So the temperature will go up just nice. But when there is samples at certain temperature, it will start to deviate because there's a reaction undergoing, whether it's endo or exo. And after it completed, it will go back to the baseline. Okay. Now, what it measures, okay, for heat flux technology is delta T. Delta T is temperature difference for comparing reference and also samples. Means TS minus TR. Get your delta T. But delta T is not enthalpy. Delta T is just delta T, means temperature differences. So what heat flux does is it will derive the delta H or your enthalpy based on the factor from the thermocouple times your delta T that's obtaining from these results. Okay, so there is a mathematical calculations involved to convert delta H, but rest assured, for user side, you don't need to do any manual conversions. The result that you are going to get is still heat flow against temperature or time. Okay, it's just that this is the working principles. So we do have another unit called power compensation or DSC 8000, 8005. Now, the design of it is different, okay, compared to the alumina furnace just now. Now you have two platinum alloy furnace. Okay, this is due to the picture, but it's actually very, very, very small. Okay, this unit also we call it as hyper DSC. Why? Later we can discuss on that because you can do very, very fast heating or cooling. Okay, due to the design of the furnace. So the difference between heat flux and power compensation is based on null principle. Now delta T is 0. What happens here is, okay, these two are your furnace. Under there, there's a sensors, and then there's a individual heaters. So what happens is, as we heat up, again, the same thing. At certain temperature, your material or your sample will start to drift, okay, due to reactions undertaken or phase transition undertaken. Then it will go back. But when it starts to drift, the sensors, okay, under the sample will start to match with reference, okay? And when there is 10 to power of -6 delta T, the sensors will start to give signals to the heaters, whether to supply or to withdraw energy to maintain the same temperature. This is why delta T is 0. We call it null principle. And how much power being supplied or being withdrawn is directly translate to delta H, means there is no conversion, okay? Because power that being supplied, you can directly measure how much is the enthalpy or the work being done, okay? So there is no conversions. You can directly measure what is the enthalpy. So this is especially good for weak transitions. For example, like TG, if you want to monitor that, okay? Or highly crystalline material, you want to measure how much is the amorphous part of the material. So this technique will be the best, okay? So this is Bakayama patented technology. Hence, it's called power compensation because it directly measures how much power being supplied by the heater or being withdrawn by the heater to maintain the same temperature as the reference temperature. Okay. So power compensation DSC is a actual power. It measures actual power energy. So we usually call it true calorimetry because there's no conversions, and because of the furnace design very, very small, you have the fastest responsiveness of the furnace. Okay, all this means you can do very fast heating, fast cooling, fastest equilibrium, okay, temperature equilibrium. And as you can see, due to the designs of it, you can do linear heating cooling. Remember I said for thermal products or thermal instruments, regardless what you are doing, it should always under control. So this technique or this unit power compensation DSC allows you to heat up your sample at 300 degrees C per minute and still within control. Okay, highest resolution, highest accuracy and precision of results due to there is no mathematical conversions. Okay. And okay, as for DSC, a very important thing is the cooling devices. So how low can you start? Because most of the time, you can start at very, or let's say you're reading TG, okay, glass transition temperature, and TG usually is at very, very low temperature. Okay, so you need to have the corresponding cooling accessories in order to allow you to start at the temperature that you want to start. Okay, so for the heat flux, we have options using this. This is what we call as a portable cooling devices. You can start at -100 because this thing is going to be filled with liquid nitrogen. Okay, of course you can opt for chiller as well. Okay, so depending on what other things that you mix into it, you can start off at -20 degrees C. But most of the time, people don't really use chiller for DSC because the starting point is too low for, yeah, not low enough, sorry, for the applications that you are running into. Okay, so generally, we will supply intracooler 2. You can start off at -70 degrees C. Okay, this is intracooler 2, means you can start your experiment at -70. Then, of course, if you want to go all the way down, you can start at -180 degrees C using the cryofill tank. Looks like this. So this is a liquid nitrogen dewar tank. So this whole thing is 50 liter. I can hold up to 50 liter liquid nitrogen. So you can start your experiment at -180. Okay. So like TGA, DSC also you need a purge gas as well. So usually we are using nitrogen. Okay, now why is it so? Although there's no decomposition, but you still want your temperature or your sample to be under a inert atmosphere, a controlled atmosphere. Hence, it is also run using nitrogen gases, inert gases. Usually it's inert gases unless you are running OIT, oxidation induction time, then oxygen is required. But usually nitrogen is sufficient regardless for your system or your sample purges. Okay. So as per usual, there's a built-in MFC as well for you to like TGA just now. And the good thing about working armor is regardless what type of thermal product you're going for, whether it's TGA or DSC, or if even STA, everybody is using the same software, the Pyris software. And the Pyris software can allows you control up to 8 units of thermal product should you require to do that. Okay. Now, this is the one that I mentioned just now. Compared to TGA, you have much more selections for DSC. Okay, a standalone DSC. So the standard would be your aluminum. So if you have a lot of volatile sample or liquid sample, this is the pen that we recommend, aluminum volatile pen. Then you do have other pens, like for example, gold, copper, or even platinum. Okay, these will withstand high temperature. Okay, so just now, like what I mentioned, DSC 8000 can go up to 750 maximum. But the thing is, aluminum melts at 600. So you cannot, if you are using aluminum pen, you cannot heat up to 600. It's going to melt inside the furnace. So if that is the case, then you need to use other types of pen. Okay, so for anybody running like metallic samples, organometallics, or even soldering materials, okay, alloys, for example, do not use aluminum, okay, because metal sample is going to react with your metal pen, forming a new type of alloy, reducing the melting point, and then fuse together with your furnace, and hence, alumina pen is recommended. So in DSC also you have alumina. So alumina means ceramics or aluminum oxide basically, okay? Then if those running evaporation studies, okay, or moisture analysis, for example, or solvent analysis, then you have a vented type of pen, allow you to, the gas that's coming out from your samples to remove from the side or from the top, okay? It's vented. So for DSC, you have another tools that you need to come together with the pen. This is called crimper, means you are going to crimp your sample, like, or seal it inside the pen that we mentioned just now. So if you have a universal crimper, so the name is universal means you can crimp different types of pens. But the thing is you need to change the insert or the head of it to crimp different types of pen. Okay, but with only one crimper, you can crimp multiple types of different pens. This is especially good for those that have different requirement on the pen or running different types of samples. So the standard crimper is only for the standard pen just now. So high pressure kit, of course, is for the high pressure pen, and also the large volume stainless steel pen using this crimper. So different types of pen do have its own crimper set as well. Okay. So for DSC, this is the calibration material that we use to calibrate the instruments. So this is the transition points. Okay. So if you run a lot of sub-ambient analysis and then you want to calibrate your materials, calibrate your instrument at sub-ambient temperature, these are the substance or the reference material with known transition points at much lower temperature or sub-ambient temperature, as you can see from here. Okay, because like just now, indium is 100 and above, right? 156.6. So let's say you are running your material at way lower temperature, then these are the things that you can consider to calibrate your instruments. Okay. So what are the applications for DSC? You can do phase transition, the general one. Of course, TG is something that most of the people are running into it. Melting point, crystallization temperature, co-crystallization temperature, crystallinity, curing purity, specific capacity, oxidation induction time. Okay. So enthalpy, like for example, your heat of fusion, heat of reactions, all these things. Okay. I'll give you some of the examples. So first we need to understand, usually these are the things that DSC is going to run into it, even your TGA as well, or polymer in general, or polymer engineering, polymer analysis. So under polymer, there's two main big groups. So you have your thermoplastics, means is reversible. Okay, if the structure is not damaged, there's no chemical changes upon heating or cooling, means you can, regardless how you are going to, how many cycles you are doing your heating cooling, as long as it doesn't decomposes, you are going to get the same results. Okay. Now, under thermoplastics, you're going to have amorphous and also crystalline. So amorphous means there is no shape to the polymer itself. Okay, the molecular chain inside the polymer is in the disordered form. So what type of polymer is amorphous? Fully amorphous. Okay, means no matter how you cool it or quench cool it, it will not be crystalline. The nature of it is amorphous. Okay, so amorphous is polystyrene, polycarbonate, polyurethane, polysulfone. These are the few types of it that's fully amorphous. So so some people might ask, like polystyrene or polycarbonate, okay, is widely used in packaging material. So packaging have shapes, right? Now the shape that you see is being manufactured by the manufacturer. That is the shape being molded. It's not the nature shape of the polymer itself. Okay, polymer itself doesn't have a shape, the chain of it. So it's called amorphous. So if amorphous material, we are going to expect only TG, glass transition temperature. Okay, so under crystalline, you have semi-crystalline and also high crystalline material or fully crystalline material, such as your PP, HDPE, or polyolefins. Okay, now PP, PE, these are crystalline material. Okay, so you only get melting and crystallization when you do a cooling. Semi-crystalline is slightly tricky because depending how you cool it, you can get your TG, you can also get your melting. So for semi-crystalline material, because part of it is amorphous, so you're going to get TG. So part of it is crystalline, you're going to get your TM and your TC as well. Example, nylon, PET, polyethylene terephthalate, and also acetal. Okay. Now this is thermoplastics, means as long as the structure is not damaged or not decomposed, then you can still get back the same TC or TM, for example, or your TG. Okay. Then we have thermosets. Okay, the chemical changes will, or the structure will change depending on the temperature or even like UV. Like for example, okay, so you have uncured or cured materials. Okay, so your rubber, your silicone, neoprene, epoxy, all these are cured thermosets, means it will not go back to its monomer form, isoprene, all these things. Okay, so uncured, you have your epoxy, polyamides, polyesters, phenolics. So these are all thermoset, and thermoset is always amorphous, means we are expecting only TG, glass transition temperature. Okay. So these are the sectors that use DSC. Even life sciences is using that as well, like your protein or the enzyme, okay, that enzyme kinetics, then you can use apply in life sciences. Pharmaceutical, of course, in general, we are still running polymer rubber for DSC, okay. All these are the things that you can actually measures using DSC. So in how's the data representation in usually in DSC? So you are going to get the curve like this, for example. So Gauss transition is always a step increase in baseline, like a staircase. Okay, so this is usually not a very strong transitions. So it's just a step increase like this. And this is why if you want to, and then if you want to get a very good reading on it, okay, it's always recommended to use a standalone DSC. Now, Glass transition being a weak transitions, notice in TGA, there is no changes of the weights, okay? Even melting also the same. In TGA, there is no changes, okay? But in melting peak, it's always a sharp transition in DSC. So exothermic going down, that means melting is endothermic going up, okay? So depend on, always read your y-axis first. So if say endo down, that means it's going to be going down. That will be melting. But normally I will represent in endo up. Okay, so exo down. So endothermic melting is always endo. So it's like a peak. Okay. So crystallization is always exo, you can see. Okay, but as per usual, regardless you are doing melting or crystallizations, in TGA there is no weight changes, hence no transitions. Okay, so this is the things that you have to be clear on decompositions and also melting, the concepts of it. Okay, for example, like your glove material, the TG usually occurs at a very low temperature, as you can see, -60 or -60. Okay, so we use DSC to check what is the TG for different types of rubber gloves. Okay. Okay, then we have what we call as plasticizer effect. Now, this example is in food sciences. Okay, so you have your biscuits. So sometimes biscuits get soggy, right? So what is the definition of TG? TG means before the inflection point. Okay, so here is glassy, here is rubbery. Okay, glass transition temperature derived from glass material. So glass doesn't melt because glass is fully amorphous. It's just from glassy state into rubbery state. So for those, you have see people blow glasses before. Okay, so at high temperature, it starts to become rubbery. Okay, becomes soft that you can mold it into a certain shape. This is why the term TG is called glass transition temperature. That means before transition is like glass at room temperature. Okay, for example, it's brittle, it's glassy. So in biscuits term, means at this stage it's glassy, it's crunchy, okay, it's brittle, but once it passes through the TG, it becomes rubbery, it becomes soggy, okay. Now, without absorbing of water or moisture from the surrounding, your TG is at 46, example, okay, or 40 something. So if I store my material at room temp, okay, for example, at 21 or 26, so it's still at the glassy state, okay? So your biscuit is still very much crunchy. But once it absorbs water or moisture from the surrounding, water by itself is a plasticizer. What does it mean, plasticizer? Plasticizer means it's going to reduce the processing temperature or usually the crystallinity of the material. So some people use this as the plasticizer for the polymer as well, not necessarily water, but something that can disrupt the structure of the polymer to reduce the processing temperature. A lot of polymer manufacturers actually do that. So now you see the TG from 40 something all the way reduced to 30 something because the structure now getting more and more disordered. Plasticize means the structure becomes more disordered. So if you keep on storing at the same temperature, of course, now it becomes soggy because the TG is already passing through the TG and go into the rubbery state, which is the soggy state. So this is for the analysis of the storage condition of the materials, okay? Next will be the polymer. As you can see, the typical curve that we can get, this is a PP container, polypropylene. So because PP by itself is highly crystalline. Now, polyolefin, PP and PE derives from hydrocarbon, means only C and H from your crude oil. So if PP and PE is fully crystalline, that means your crude oil, okay, means from oil and gas, your crude oil, those are also fully crystalline material. So your wax, okay, now why you need to prevent wax from form inside the crude oil during the transport? Because itself is crystals. Wax by itself is a crystals, means it's a crystalline form of the crude oil. Okay, that is the wax that you see inside the transfer line. So this is why PE, PP is always highly crystalline materials, and you will see melting and also crystallization. When you do a heating, you get melting. When you do a cooling, you get recrystallizations of your material. No TG, right? Because this is fully crystalline material. Now, this is a slightly tricky example. So you have your PET, which is a semi-crystalline material. So as what I mentioned, semi-crystalline material will have TG, okay, because the amorphous part of it is represented by the TG. Then you have your co-crystallization, especially when you heat up slowly. For example, 10 degrees C per minute, the conventional heating rate. So after it passing through TG, free volume increases, the molecular chain now can move around. So, okay, the general rules are, if a material can go to crystalline form, it will go to crystalline form because crystalline form is more stable than amorphous form. Hence, even you are doing a heating, the molecule inside will start to arrange themselves, means start to crystalline, means arrange themselves into an ordered manner. Okay, but this is a metastable state, means at a higher temperature, it is going to melt. Hence, for semi-crystalline material, if you heat up slowly, you are going to get TG, recrystallization of the molecules, because now you are allowing it time to recrystallize or repack itself into a crystalline form, and then melting at a higher temperature. So this is the typical curve you're going to see. So if I don't want to say this, what I can do is I can heat up fast. But this, of course, like what I mentioned just now, depend on how fast can your instrument heat and cannot be losing control. Always remember, it is under a control state. So with a DSC 8000, we can heat up to, like, for example, 300 degrees C per minute. Then it's going to suppress the crystallization and straight away to melting. So for very, very fast heating, you wouldn't see crystallization anymore. Okay. You can do for failure analysis as well. And in fact, this is true cases, okay, for logistics for Coca-Cola company. So they noticed that the bottle breaks easily, okay? So they investigate what is actually happening to the bottles itself. So we actually sample different parts of the bottle. So you have your lip, you have your shoulders, you have your sidewall, you have your bottom. So we noticed that the sidewall and the shoulder means this whole part is actually very crystalline. You can see. Okay, so it's very crystalline. But for crystallinity, these things is not for polymer especially. It's not really the higher the crystallinity, the better it will be. In this case, because crystallinity will affect the strength, the flexibility and clarity, and also the most important is your impact properties. The higher the crystallinity, the more the material acts like a glass. It's going to shatter, it become more brittle, lower mechanical strength, okay? So that means upon impact, the bottle now, instead bounce like a plastic that you normally see, it breaks apart like a glass, okay? So once it comes into impact, it broke. So this is why they need to check the production site for the bottle itself to reduce the crystallinity or to adjust the crystallinity of the product themselves or the packaging themselves, okay? So DSC is also applied in food as well. Okay, so this is CBE. CBE is cocoa butter equivalent. So the cocoa that you eat, okay, like that you like, for example, Hershey's or Ferrero Rocher, all these things, it's actually most of the time it's not really cocoa butter, it's CBE, cocoa butter equivalent, okay? And there's two major forms that exist inside cocoa butter, okay? You have your beta prime form and your beta form. Okay, so your chocolates, they do not want it in this form. So they're going through a tempering process. Means they are going to temper the material under a certain temperature and then adjust the form into what they want. Usually it's the beta prime form. So after tempered, then they use DSC to check, okay, now this is the form that they want or the manufacturer wants. Okay, so the slogan, the chocolate, they said that the chocolate melts in your mouth, not in your hand, all these things, is because it exists in this form. Okay, that's why it tastes soft and then it melts at a lower temperature. If everything is in here, it's going to taste like brick. Okay, and it's also not going to melt anytime soon. Okay, so this is how they control from the food sciences as well. Then, of course, like what I mentioned just now, this is low temperature epoxy curing materials. So when it's not being cured, okay, so it's going to heat. Okay, curing, remember I shown just now, is a chemical process, is irreversible. Okay, and then it is always exothermic because new bonds being formed. So you only get the curing peak once. Okay, and then you cool it back down, and when you heat it up again, now you can see your TG. Why? Because thermosets or cross-linking material is always amorphous, hence TG. And when it is fully cured, you will not see the curing peak anymore. So this is a thermoset material. This is not thermoplastics. So if it's a thermoplastic, it is crystallization, because crystallization is also exothermic. Regardless how many times you cool, you are going to see the crystallization peaks. Okay, but not for curing material. Curing material only once. Once it's fully cured, it's become flatline at the same temperature, as you can see. So this is not a reproducible transitions. Okay. So people use the TG as the curing degree as well. So the higher the TG, the higher the curing or the cross-linking percentages of the material. Okay, as you can see, at higher temperature, it's more cured, lower temperature is less cured. Or you can use the curing peak as well. So curing peak is always exothermic. So just now you can see for fully uncured material, it will going to have a very big uncured peak. So the more or the higher the curing percentages is going to reduce and reduce until you get a flat line indicating that the material has fully cured. So you can use DSC as a check for your curing degree of the materials as well. Okay. Okay, this is OIT. So it's a standard test for polyolefins. Okay, means how long can the polymer actually withstand oxygen attack before it get oxidizes. So the method states that oxygen is required definitely because you need it to, and then this is an open pan analysis because you need oxygen to come into contact with the polymer itself. So of course you're going to heat up and then the material is going to melt and then isothermal. And then after that at 200 degrees C, switch over to oxygen and start observe until the exotherm, because oxidation is also exothermic and irreversible. So oxidation induction time, we are going to take the time how long from the point that you switch over to oxygen to the point where the exotherm comes out. This will be how long it takes for your material to get oxidized. So this is a standard test. For example, your water piping, like for example, applied by Shabas. Okay, they use this to check the HDPE piping, the water piping, okay, the polymer, and the OIT must be longer or equivalent to 80 minutes. Okay. Okay, we're talking about crude oil just now. So you see crude oil. So one of the things that they measured is what they call WAT, wax appearance temperature, or WDT, wax disappearance temperature. So they, for oil manufacturers or oil processor, they need to know what is the wax appearance temperature. Okay, so when they heat up to melt and then they cool down slowly, okay, so you're going to get your recrystallization temperature or crystallization temperature or the crystallization peak. Okay, we do not take the peak point, we measures the onsets. That means for the crude oil transfer line or the transfer tube, in order for it to, or in order to prevent recrystallization inside the transfer tube, causing blockage and everything, we need to maintain the temperature higher than the onset temperature. Means, for example, this crude oil starts to crystallize at 26 degrees C or 27, means your transfer tube or transfer line must be higher than 27 in order to prevent the crude oil from recrystallize inside the transfer line. Okay, so this is what they want to do, or this is the wax appearance temperature application. Okay. In fact, you can know how much of the wax is going to precipitated or form from the crude oil by using DSC as well. So we have different standard crude oils with known value of wax percentages. Okay, and then we subjected to DSC run to determine what is the peak. Okay, the peak area. Sorry. So the peak area of the crystallization point. Okay, so from here, wax content versus what is the peak area for the crystallization peak, you can plot a calibration curve. So next, you can run unknown sample, okay, or unknown crude oil to determine how much is the wax content presence within the crude oil, or that unknown crude oil, using this set of calibration. So when calibrations are involved, that means quantitation is required. Okay, so from if you have a standard with known wax content, then you can plot a calibration curve using DSC based on the peak area, okay, joule per gram, the enthalpy of the crystallization peak. So for those doing specific capacity, we are using a three curves method. So you do need to have a Sapphire this standard. So this will have a known specific capacity. So we need to run three runs. One is the baseline run, one is the Sapphire, and one is the sample run. So the temperature program must be ISO, scan ISO, depending on your temperature range. But there must be two steps of ISO steps at the initial and the ending of the run. Okay, so after this, you can just fit all these three curves into the software, and then it will calculate the specific capacity for you. It's something like this. So this is the curve from the Sapphire standard. This is from with sample. So this is just baseline. Baseline means empty pan only. Okay, when you have all these three curves put into the specific calculation software, and then it will give you the CP curve or the specific curve for the sample. Okay, so now we can mark what is the temperature that we want together with what is the specific capacity. So for DSC, we can also do isothermal crystallization kinetics. So as per usual, like what I mentioned just now, so we are based on 6 curves method. So if you are using kinetic, at least 3 curves, maximum 6 curves in different heating rates, or in this case, because it's isothermal, means I'm holding it at different isothermal temperature. Okay, so they want to know what is the crystallization kinetics for the crude oil. This is also crude oil. Okay, so 6 curves. Okay, then what we want to get is the N and also the KT, the intersections. This is the crystallization rate constant, and this is the nuclei growth mechanisms. So you can see different isothermal temperature being held. Okay, 5 curves or maximum 6 curves. So these are all generated from the software. Okay, and then fit into this software. You can fit into the KT, fit into the order of reactions. Okay, the N. Then we calculate what is the half-life. So want to determine what is the crystallization half time, or the how fast is your crystallization. Okay, so half time is defined as the extent of crystallization completed at 50%. So from here, with increased crystallization temperature, the T half increases, means it takes longer at lower, at higher temperature, it will take longer temperature, a longer time for it to start crystallization. Okay. So higher crystallization temperature, lower supercooling degree. So the nuclei for the crystallization are more difficult to form. So for crystallization, there's two mechanism or two kinetics. One is with the nuclei or the nucleus growth. Another one is aggregation or agglomerations of the particles within the material or the samples. Okay, so if you have nuclear crystallization, then the particle size will be small. If you have aggregation, agglomeration, usually you will have big particle sizes. So from here also you can deduce what is the crystallization mechanisms. Then you can also use DSC to do quantitative methods or quantitative analysis of different polymer blends or copolymer blends, okay, like LDPE and LDPE. So LDPE and LDPE actually have different crystallization peak, okay. So from here, if we cool it down very, very slowly, we can allow the LDPE and LDPE to segregate, okay, more completely. So we can actually plot the calibration curve based on the peak height ratio of, means peak height ratio of LL and LDPE, okay? So percentage of LL inside, what is the peak height ratio between these two peaks? But in order to do this, because you need to allow it to segregate completely, you need to use a very slow cooling rate to allow good separation of LD and LDPE, okay? So this is hyper DSC, only for DSC 8000, 8005, the power compensation. So we can now do linear control scan rates many, many times faster. You can go up to 500 degrees C per minute if you will, okay? So you can, and still within control compared to the conventional DSC. So what we measure is, of course, is milliwatts. So watt equals joule per second. So the faster that you heat it up means time drop W, because W equals joule per second. Decrease S, increase W. So you can use this to increase the sensitivity, okay, of the signals. Okay, let me show you the examples later. So, okay, for those familiar with DSC, okay, usually you have a transient point or the starting point. Okay, so anything that transition here, you cannot use it as a data because it's going to be overlapped by the equilibration period of the furnace as well. So for heat flux DSC, it takes longer, you can see, until it starts the first data capture. But for power compensation DSC, the equilibration period is much faster, and then you can detect the first transition at a much lower temperature, which you don't see in heat flux. And then even you can see, you cannot determine it because it's being overlapped by the equilibration period as well. Then the signal is much better for the second transition as well. And this is why we said power compensation DSC has a better sensitivity and the fastest equilibration period as well due to the furnace design. So what is the advantages of it? Enhanced sensitivity, identify low energy transitions. You can use very, very small samples. And for very, very low amorphous material, TG basically, you can use hyper DSC, eliminate artifacts from the slow scan, like for example, the recrystallization that we mentioned just now, simulate processing condition and separate overlapping events as well. Okay, so this is enhanced sensitivity. You can calibrate at different heating rates. Okay, this is important. If you want to use a very fast heating rate, you need to calibrate at that particular heating rate. So like what we have mentioned just now, W equals joule per second. The faster you go, the bigger the peak will be. So you can apply this concept onto this. For example, PMMA is a semi-crystalline material with a very weak TG. You can see even you heat up at 50 degrees C per minute, the TG is so weak, the signal. But okay, remember W equals joule per second. As we increase the heating rate, the time for analysis becomes shorter, the signal increases. So we can use this to confirm the transitions of your material at that particular temperature. Because even if you use 50 degrees C per minute, you hardly can see the transitions. But with 500 degrees C, now this is very obvious. This is the TG for the PMMA. Then you can use this for simulating quench cooling, okay, from the melt. Okay, so this is a polyester material. It is also semi-crystalline material. So first heat, okay, first heat, semi-crystalline, you see, we heat it up at 40 degrees C per minute. Heat it up. Okay, so no recrystallization because the material is crystalline to begin with. But now if I want to make it more amorphous, what I can do is from 300, I cool down very rapidly to 40 degree again. Then I reheat it up again. This is second heating. Now I can see my TG. And because slow heating, right? So it will recrystallize again and then melts again. But of course, because now it is more amorphous, hence your melting is reduced compared to the first heating as we have received. So this is why I say semi-crystalline material, depending on how you heat and how you cool it, you will get drastically different results. Okay, this is not wrong. This is just how you prep your sample or how you run your materials. Okay, and usually this is only for semi-crystalline material. If the material is fully amorphous, only TG. If it's fully crystalline, it's going to be melting peak and also crystallization peak. Okay, so you can use this to simulate the processing condition. So now in industry, usually for polymer engineering, they wouldn't cool down slowly, for example. Usually they will, for example, injection molded, they will do quench cool. Okay, so this is the product coming from the injection molding. So this is the melting peak. Means the plastic or the polymer is going to get melted, and then after that quench cool in a very, very fast rate. And then this is the result. So we can use DSC to simulate that as well for the PA6 nylon. So what it does is we are going to melt it, and then we're going to cool it down so fast, like what we did just now with this at a very, very fast rate. And then the end product, we are going to reheat it up again. So now the melting point is actually comparable to how we did it in injection molding. Okay, so we can use DSC to simulate the processes as well. And even detection of trace impurities. Now this is for polymorphism material. Okay, if you scan it normal, okay, for example, like 10 degrees C per minute, you only get one form 1. This is carbamazepine. It's a the ubatan sakit, they call it. Okay, so this one you have form 1, that which is the form that they want. Form 3 is something they don't want. Okay, so now drugs can be existing in multiple form, especially we call it polymorphism. So some form is either useless or toxic to human health. Okay, so they need to confirm the form that the drug existed. But as you heat up in with a high heating rate, now form 3, remember I said the faster you go, the signal will become higher and higher. Okay, W equal joule per second, so increase sensitivity. Now they actually found out that the drug actually exists in form 3 as well, which is not tolerable by human body. Okay, so this is how they confirm for polymorphic materials. So like what I mentioned just now, for semi-crystalline material, if you heat up at a normal heating rate, it's going to recrystallizes and then melts. Okay, but if you heat up very, very fast, you can suppress the recrystallization. So the material wouldn't have time to recrystallize and then it will melt. So this is the true nature of your material, because in real life, your end product doesn't segregate, or it doesn't recrystallize into different forms. Okay, it should just melt with the heating rates that we are supplying. Okay, so usually only high heating rate can suppress so this will reflect what is the true nature of your end products. Okay, so this is one example from Proton. Basically, they claim that they have 2 batch of materials, raw materials, okay, polymer. So when they heat up, so one is okay, one is not. So when they heat up, when you heat up, this is the melting, this is the crystallization. So both results are comparable, or there is not much difference. Okay, unable to detect significant differences using the conventional heating rate or cooling rates. So 10 degrees C, 20 degrees C. But during the processes, it actually found that one batches is actually contains issues of it. Okay. So what we did is we melt the materials at 220, and then after that cool very, very rapidly back to 140 and hold isothermal to monitor the crystallization kinetics. Now we can see that the time for this problematic material, actually it crystallizes much faster compared to, this is time, okay, compared to the red batches. Okay, so we know that this is the problematic batches, means it crystallizes at a higher temperature whereby it shouldn't did so. Means this is going to affect from the production side. Okay, so using isothermal crystallization, we can clearly see the differences compared to the conventional scanning, heating or cooling. So another one is if you heat up at 10 degrees C per minute, for example, nylon is highly hygroscopic, means it's going to absorb a lot of moisture. Okay, and when you heat up slowly, all you get is one big hump like this. Okay, so this is indication of water losses or moisture losses. So nothing is being observed. So using a very fast heating rate, we can actually split. Means the water losses is going to be pushed to a higher temperature. Now we can see TG and we can see melt, because melt is definitely going to be at a higher temperature. So you see your TG, you see your moisture, you see your melting peak, which is not observable if you're using a conventional heating rate like 10 degrees C per minute. Okay. So this is the standards. The last part will be hyphenation, just some additional information for you. Okay, so like what I mentioned just now, we have TGIR. You can hook it up with TGMS as well. So any our TGA, you can do that. Okay, TGIR, TGMS. So this will give you the quantitative results, means the weight loss percentages, and this IR or MS or GCMS even. Okay, depending on what are the detectors that you hook it up with. Okay, this will give you the qualitative result. Means the gases that's coming from TGA, you can flow it into GCMS or IR to do identification. Okay, based on breather retention time, mass overcharge ratio, or even the functional group from IR spectrum. Okay, example. Okay, for example, this is running using TGIR, running a PVC material. So PVC is polyvinyl chloride. So the side chain is hydrogen chloride. So this is coming from TGA. So the first weight losses, second weight losses. So the black curve is what we call as a Gram-Schmidt plots. So the highest point, each of the point that you see is a spectrum from the IR scan. Okay, so correspondingly, we take the highest point, which is the first decomposition, highest point for the second decomposition, then we extract out the spectrum. So the first spectrum after match with library, it tells you that it's hydrogen chloride, which is from the decomposition of the chloride side chain of PVC. And then you have your main brain chain break off, okay, of the polyvinyl with a matching score of 0.99 against the IR library. Okay, so now we can see that this is where the polymer break off, this is where the side chain evolve. So you get your identification together with how many percentages of each component within the materials. Okay. Then we can run it for a more complex material. So this is paint. So paint usually is very complex. It consists of multi-components. Okay, and you can see there's multi-component stages of weight losses in your TGA as well. So from each of the Gram-Schmidt point, we can extract three absorbance or three spectrum. So the first spectrum occurring at 130 degrees C, the first weight losses, is corresponding after matching with libraries, is corresponded to the propylene glycol. Okay, so it's the additives that added into your paints. Next is your okay, so this paint claims to be your antifungal claim, antifungal paints. So the second weight losses at 235 degrees C is actually matched with sulfonamide or benzene sulfonamide, which is an antifungal agent, okay, added into the paint. And then the main paints, okay, paint you have multiple types. So we want to know what type of paints is this. So for the third decomposition at 345 degrees C, it matches with a metal methacrylate PMMA. So we know that this is acrylic based paint materials. Okay, so the TGIR, another attention I would like to bring you is we now have a new accessory. It's an in-compartment TGA. So TGA now works like a accessories inside a FDIR. So everything is in one boxes only. But of course, it's not wrong if you have a conventional TGA flow into the separate IR. It works as well. This is just the latest addition to the hyphenation technology. Now you have TGGCMS as well. This is for failure checking or failure analysis of synthetic dyes against a good dye. So we have, okay, I'm not sure how well versed is everybody here for GCMS, but what we detect is actually the retention or the chromatogram. Okay, what you get is the chromatogram. So we run a good sample and then the defective ink samples, and then we actually notice that there's a difference in this retention time. Then from here, we extract it, mesh with the MS libraries. We identify it as 2-naphthol. Okay. based on the mass overcharge of 144 in this particular retention time. And then based on the peak area, we can do a ratio. So you can see that the defective die have an addition 5 times more of the 2 naphtol addition. Okay, so additives is 5 times more compared to the good die, hence causing it to have a failure performance. Okay, as for other decomposition, so you can see different regions of decomposition coming from TGA, but other region all matches well except the first, means it added in a lot of maybe a plasticizer or maybe additives into the defective ink. Okay. Then we can use TGGCMS to check the phthalates in PVC as well. So from TGA, we can obviously see differences. Okay, so the banned phthalates has a higher percentages of phthalates. Then the the regulated one or the non-banned has a lower percentages, but we do not know what type of phthalates is inside these PVC materials. Okay, so phthalate is a hormonal disruptor. It must be regulated because it's highly toxic to human health as well. So from the GCMS data or from the GC data or the chromatogram data, you can obviously see that the without banned phthalates is much lower concentration because peak area indications how high is your concentration as well, okay, or the component of it. So for the phthalates, the banned phthalate is much higher. So now we want to know what is the fragments of it or what is the banned phthalate. So we match with the taking this retention time, we check with the MS library, the NIST library. It actually tells us there's a benzene and also 2-ethyl hexyl chloride. Now this is actually DHP, okay, is a plasticizer or is the phthalates that's been added for the PVC processing. So they actually add more into the banned phthalates in order to reduce the processing temperature. So you can use this to double check your materials as well. Okay. So that concludes my presentation. Any questions? Thank you very much.
Sila tak dengar. Still tak dengar Sila. Tak dengar Sila.
I think I'll take the questions from the chat
From
first.
chat.
Okay, Sila
Okay.
dengar. Okay, yes.
Okay,
Sekarang dengar ke?
so
Dengar.
yes.
Sila
Alright.
dengar.
Okay, Doctor,
Okay.
you can continue with the Q&A.
Yeah, sure.
Okay.
Thanks.
Sorry.
Okay, so now the first question also, what is the exact, is it the first question? Wait, I don't think that's the first question.
The first question
Okay, yeah.
is
When performing, right?
Yes.
Okay. When performing TGA tests for different samples, the weight of the sample must be the same. No. If you just want to do a survey scan, for example, you don't need to do that. But for comparison studies, yes, please do that because you use a different weight of samples, especially huge difference, then the result is not really comparable because it's going to have a different thermal lag and different resolution as well. So, of course, to make it simple, just make sure that if you want to do a comparison studies, or if you make it a habit, just run in 10 or 50 milligrams of the materials of your sample is enough. Okay, it's not really encouraged to add a lot of samples into the run, especially like more than 30 milligram, for examples. Even you can do that, please don't, because you're going to introduce a lot of thermal lag, means you are going to affect the resolution, and also the temperature profiling will not be accurate as well. You are going to affect the decomposition kinetics as well. Okay, so general guideline is 10 to 15 milligram is good enough for usually for most of the applications, unless you are talking about very, very low level or very, very minute changes that you want to see where you use 15 milligram samples you can't see, then you can afford to add more in. Okay. So also, what is the exact temperature to stop performing the tests? Okay, you can only run up to the maximum temperature of the instrument allows you to go. So depending on what instrument that you have, so that is the maximum temperature. So I would say, but if for organic material like polymer, like your oil samples, like what I shown just now, usually 600, 800 is way more than enough. The determining factor here would be what are the purge gas you use. That would be the most important thing in fact. Okay, unless you are talking you are running metal samples, then of course even you run to like maximum temperature also it will not have any changes because it is highly stable. Or glass sample, quartz material for examples. But let's say you're running polymer, typically 650 is good enough. And then if it forms a lot of carbons, please switch over to oxygen. And then maybe heat up to 800, then most probably you can stop your reactions. Okay. Can TGA be used for metal alloy? Yes, can, depending on what are the applications that you are looking into it. If you want to analyze metals, then no, this is not the correct way. But let's say you are running polymer coated on metals, you want to determine what is the polymer percentages, then yes, TGA will be a um, good tools to do that. Okay, but if you want to determine what is the metal percentages or certain element inside your metal, then no, that is the job for example, like ICP MS or ICP OES. Okay. Can we use pure nitrogen as a purge gas, you mean? No, because hydrogen is highly combustible. It's not recommended. You can, but it's not recommended because it's highly reactive. Especially when it comes to contact with oxygen, you are going to get explosion. So please don't use hydrogen. But if you want to use a small molecular weight carrier gases, helium is another good choices. Okay. Do you offer kinetic as part of the normal software or needed to buy separately? Okay, now the kinetic software is included if you already have a higher end model, like for example, TGA 8000. So it's already inclusive. Okay. For those don't have, if you want to upgrade it, we have to check whether your software version is compatible and also your instrument, whether it's compatible with that. Okay. What if I get slope line instead of horizontal line? I'm sorry, this I will need to get more context. What do you mean by slope line or horizontal line? And which instrument are you referring to? Is it TGA slope line, the baseline of it, weight losses, or the DSC heat flow?
I think this one
Baseline.
is for TGA, Dato' Win.
Okay, for TGA. TGA slope line means the sample contains a lot of volatiles, means even before you start running, it start to have a lot of weight losses already. That's why you didn't start off with a flat line and then suddenly everything will go down very quickly. Means this material is highly volatile. This is usually the indications of it. But we are talking about weight losses still. If you get weight gain, that's another story. Weight gain means there are something that gain weight, especially if you like flow in oxygen, okay, then oxidation occurs. So when oxidation occurs, weight density will increase, hence you'll notice there's a weight gain. In TGA, normally we don't observe weight gain, okay? We want to see weight losses because that is decompositions, okay? Now, another slope line that what I mentioned just now is might be due to is the buoyancy effect, the convection, okay? And this usually occurs at the initial start analysis. So what you can do here is, if you do not have the features that I mentioned just now, the one that you have a quartz tube, because that's TGA 8000's features, you actually can run empty baseline. And then you use the baseline subtraction method to get a better baseline performance, okay? So, but in order to run baseline means the temperature program setup is exactly how you're going to run your samples. Okay, it's just that empty without any pen inside. Okay, that will be your baseline and it's going to save as a data file as well. So apply it when you want to run your sample. Okay, in your setup, there is what we call as automatic baseline subtraction. So add in the file of the baseline file, and then it will subtract the baseline for you when you run your sample. So this will reduce the curvature of the baseline or the thermogram. Now, in the TGA curve, which point denoted the degradation temperature? Okay, so when you see your weight losses curve just now, right? So you call out the derivative points or the derivative curve, and then the sharpest transition points or the inflection point will determine that is your degradation temperature from the derivative curve coming, or the DTG curve coming from the thermogram of your TGA. Okay, it's a mathematical calculation. It's called derivative curve. I'm having issue interpreting a DSC test. Can I share my screen? I think so, but I'm not the. Maybe I just need to stop the sharing first. Maybe the moderator can.
Maybe we will have the quick one.
Oh, okay.
Okay.
Yeah. So I'll
So you can
stop
share
sharing.
you can share the screen. You can share your screen, Mr.
Yeah.
Amadi.
Okay.
Okay.
Okay, the challenges I'm having is, first, there are two plots here. Can you see my screen?
Yes.
Yes, but it's very small. Can you enlarge
Maybe
your
you
thermometer?
can zoom in a bit more. Better.
Okay. First, I want to know what is the implication of the differences in heat flow, because one of them signifies cooling, while the other signifies heating.
Okay. Okay. So you answer.
First,
You answer these first. So how do you determine which one is exo, which one is endo? Hello.
Sorry,
Yeah.
are you asking
Which?
me how?
Yes. I'm asking right now. Which one is exo? Which one is endo?
Exo should
The
be the
red
red
one
one,
or the? Is it? Okay.
because the red one.
For DSC curve, what you should read first? Remember I mentioned just now, for DSC interpretation, you should always, or heat flow interpretation, you should always read your y-axis first, right? Now notice at the left corner there, there's exo up. That means your blue curve is actually exothermic. Your red curve is actually endothermic. That means the red curve is actually the melting peak. The blue is actually the crystallization.
Okay.
You get what I mean?
The blue is the crystallization.
Yeah, because
Why?
it's exo up. So anything pointing upward is exothermic. Crystallization is always exo. So blue is actually exo, red is actually endothermic. So red is actually melting. This is a polymer material, is it?
This is a nitinol, NITI.
Okay.
Yeah. Then secondly, the point where there is a straight line, does it have any implication on the description of process, or where
Straight
you
line
just
means
focus
there
on
is
is
straight line means there is no transition happening. That's it. But you do want a flat baseline so that you can construct your baseline for the peak. And the way that this is constructed, this is actually, I wouldn't say not correct, but we don't usually construct it like this. You can actually get your starting point, means for that peak analysis, you can actually get your start, your end, or what we call as onset, the end, and also the peak, just by using the peak area function. You don't need to plot your onset for your start, your end, and everything. Yeah. So you can plot a straight line through, then form like a triangle, means from flat to flat, to construct your baseline, and then it will auto calculate your starts. I mean, here is indicating starts lah. But usually we call it onsets, and then the finish is ends, and then the peak point, and also what is the enthalpy for this peak. I believe this is not a Perkin-Elmer system. Correct me if I'm wrong, but yeah, typically the analysis is based on that. So you need to plot calibration. You need to plot the peak. So we do not really plot it like using the onset features, because the end is not really onsets. And yeah, so if okay, this is why I said you should determine make sure you have the correct endo up or endo down first, because now everything is in inverse. So your red curve now is actually finish, is actually your start is actually your finish. So it's the other way around now.
Okay. Maybe
Yeah.
we can have like another one question, because we are running out of
Yeah.
time.
Oh, yeah, so
we
sorry.
have another 2 sessions later on.
Yeah.
The rest of the question, we can ask Dr. Uy later, and I will share with you the answer later on. Is it okay?
Yes,
Okay.
yes. Thank
All
you.
right. Okay, thank you very much, Dr. Uy, for very informative sharing. And next, I would like to invite Madam Faiza to share with us on the sample preparation for TGA and DSC that we usually do in CAL. Okay.
Okay, you see in here?
Nampak tak?
See?
Yes.
You can see? Yes.
Yes.
Okay. 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 Assalamualaikum and good afternoon, everyone. Okay. Actually, I would like to show you sample preparation for TGA equipment and equipment demonstration.
Kak Ija tak dengar.
Tak dengar? Okay. Okay. Dengar tak? Dengar?
Bukan, video tu tak dengar. Suara Kak Ija
Oh, okay,
dengar.
okay. Okay, okay, okay. Yeah, I can get back. Okay, firstly, okay, this is our model, brand packing Elmer, model STA 6000. Okay, for your information, this video actually I run the testing run manually because the model can run auto sampler, but for this time I run for this sample for manually. Okay. Okay, for your information, actually for this analysis for TGA, important for me to know your analysis. That means your heating range and heating rate. So I must key in your request for heating range and heating rate. This one you can see lah for the method analysis for initial temperature you required. Okay, these are set crucible. Okay, I run this sample manually. I must press 0 weight. Okay, this sample is powder. Actually, for TGA, you can send sample powder and liquid. For demonstration today is for powder only, powder sample. Only small amount. Okay, for TGA minimum weight below 20 mg, but you can send sample below 20 mg for sample powder. Okay, that's all. Very simple video from TGA equipment. Okay, I would like share to another equipment, DSC equipment. Okay.
Macam
Yeah.
kena share balik semula and include computer sound tu.
Oh, alright, right. Wait, Okay, wait, sorry. Okay, this video for DSC. Okay, DSC. I would like to share you video for sample preparation and equipment demonstration. Okay, the person just is Mr. Shairul bin Harun. Okay, we have two types sample here, liquid and solid sample. This is
Okay,
for
dengar
liquid.
dah.
This for liquid sample. Okay, this is for solid sample, powder sample. Only small amount. We put in T0 pen. Okay, we cover the sample using T0 press. Okay, for your information, we need to remind to our customer they must perform the TGA analysis first to get the temperature composition when they can set up lah for the AC analysis. So before you like to do the testing for the AC, we suggest and propose to you for TGA analysis first, yeah. Reference sample is, that means empty sample. Okay, that's all. This is a video for the DSC. Okay, if you wish to re-show again, you can go to LMG video at YouTube LMG, UTP video LMG. Okay, that's all. Sheila, any question you can read at chatting box.
Okay, thank you, Puan Faiza. Okay, next we will proceed. Very quick one on the last session, which is on the booking procedure of TGA and DSC, as well as other equipments available at CAL. Okay, so basically, okay.
Okay, nampak.
Okay, so basically, all of the customer can submit their request for TGA as well as DSC in ULab, right? So just log in ULab, go to the request services tab and submit your request. Then after that, all of the PIC, CAL PIC will issue the quotation. So then you just need to agree with the quotation and proceed for submit, and then submit the quotation to your supervisor, so that they will request, they will submit in your research, and once we get the approval from your research, then only we will proceed with the assignment of the testing slot. Okay, so when you have the testing slot, when you have the date, then only you can submit the samples, and we will proceed the testing on the day of the booking date. And after that, after finish the testing, we will share the results via shared drive, and then only we will proceed with the back charging process to the call center. Okay, but however, for TGA and DSC is considered as non-chargeable testing, where we did not charge for FIP and also postgraduate samples. But usually, but we only allowed limited number of sample for each booking. Okay, all right. So all of the equipment video and also the recording of the this webinar, we will upload it in UTP LMG channel, so you can subscribe, and later on you can always refer to the to our YouTube channel. All right. Okay, so that's all for today. I wish to thank Dr. Uy for spending his time and for today's webinar. And we do really hope that you gain something through this webinar. And if there is any question that you want to clarify on TGA and DSC, you can just drop in the chat session. If Dr. Uy, because Dr. Uy, maybe later on he can't access the team, because he actually from Pekin Elmer. Okay, so but if you have any question, you can just inform us, then we will email directly to Dr. Uy. Okay, so that's all for today. Thank you for your time, and Assalamualaikum.